welcome to everyone. Good morning to respected Dr. Paresh Patel sir and dear participants. Myself, Khushbu Desai, I on behalf of KBS and NATARAJ College Vapi, welcome you all for the exciting fourth session on symmetry and group theory in chemistry and its applications. I extend my sincere warm welcome to resource person Dr. Paresh Patel sir for today's webinar. Sir, the previous live session of your lecture was very engaging and interesting. We are very grateful to you, sir, for all your efforts given to the students. Now I request Dr. Paresh Patel sir to continue further with today's lecture. Over to you, sir.
Thank you, Khushbu madam. Good morning, all of you. So, in the previous lecture, we discussed about the how to represent or how to construct the matrix for the different symmetry operations. Yesterday, we discussed about the matrix representations for the identity symmetry operation, proper axis of symmetry, anti-clockwise as well as clockwise. Then we also discussed about the plane of symmetry, then improper axis of symmetry, and matrix representations for the center of symmetry. Now, and we also discuss about the reducible and irreducible representations. So today we are going for the relationship between reducible and irreducible representations. We know that if we convert higher dimension matrix into lower dimension matrix, so that representations can be represented as a reducible representations, and we can't reduce the higher dimension matrix into lower dimension matrix, so that representations can be represented as a irreducible representations. So dear students, uh, relation between reducible and irreducible representation can be represented by Ni is equal to 1 upon h summation of character R into R into N character I into R. This is the relationship between the reducible and irreducible representations. Ni means numbers of time that irreducible representations. S represents order of a group, and this is the summation of character R into R. It means this is the character for reducible representations and represents number of time that symmetry operations, and character I into R. This is the character for irreducible representations. So dear students, this is the relation between reducible and irreducible representation. Ni is equal to numbers of time that irreducible representations. H represents order of a group. This is the character for reducible representations. N is equal to numbers of time that symmetry operations, and this is the character for irreducible representation. As for examples, if we convert one reducible representation into irreducible representations, so with the help of this equation, we can reduce any reducible representations into irreducible representations. So dear students, this is the one reducible representations. Why? The dimension of this identity symmetry operation is 5. Now we have to convert these reducible representations into irreducible representation. So for this, we require to convert the reducible into irreducible representation, we require a character table for C3V point group. And we know that the character for C3V point group, C3V E to YC3, 3 sigma V, A1, A2, and E. 1, 1, 1, 1, 1, minus 1, 2, minus 1, 0. So this is the character table for C3V point group. Now we have to convert this reducible representation into irreducible component. So with the help of this equation, first of all, we have to find out the values of N1, N2, N3. N1 which corresponds to one irreducible representation, N2 which corresponds to a two irreducible representation, and N3 which represents the it corresponds to N3. So N1 corresponds to A1 irreducible representation. So N1, we know that H represents order of a group, and order of a group is equal to numbers of that symmetry operation in the molecule in that group. So E1, 2, C3, 3 sigma V. It means order of a group for C3V point group is 6. Why? C3V point group consists 3 symmetry operations or elements. Okay, so 1 by 6. Then we have to go for the summation of character reducible. It means 5. Then numbers of that symmetry operation is 1. Again, character for irreducible representation. So this is the character for irreducible representation. Character for identity is 1 plus 2. This is the character for reducible representation. This is the numbers of that symmetry operations. And 1 is the character for irreducible representations. Again, minus 1. This is the reducible representations. And numbers of that symmetry operations. And character for irreducible representations is equal to 1. Is equal to 1 by 6. 5 plus 4 minus 3 is equal to 1. So value for N1 is equal to 1. Similarly, if you go for the value for N2, so N1 which corresponds to A1 irreducible representation. Now, second one is A2. N2 is equal to 1 upon 6. Order of axis is equal to 6. Now, summation of character R. So, the value for character R is 5. Then, numbers of symmetry operation is 1. And then, character for irreducible representation is equal to 1. Plus, this is the character for reducible representation is 2. 2 is the numbers of that symmetry operation and 1 is the irreducible component. Plus, this is the character for reducible representation. Numbers of this symmetry operation is 3. And character for irreducible representation is minus 1. Is equal to 1 by 6. 5 plus 4 minus plus 3. So is equal to 2. So the value for N2 is equal to 2. Similarly, if you go for the N3, N3 which corresponds to E. 1 by 6. Order of a group is equal to 6. Now reducible representation is 5. Numbers of symmetry operation is 1. And character for irreducible representation is 2. Plus, this is the character for reducible representation. Then numbers of the symmetry operation is 2. And again 1. Plus, character for reducible representation is minus 1. Numbers of that symmetry operation is 3. And irreducible component is 0. So is equal to 1 by 6. 10 plus 4. Just a minute. This is minus 1. It means minus 4 plus 0 is equal to 1. So the value for N3 is equal to 1. So with the help of relation between reducible and irreducible representations, the values for N1, N2, N3, N1 is equal to 1, N2 is equal to, N3 is equal to 1. C3V. E, twice C3 and 3 sigma. Okay, here N1 is equal to 1. It means the value for N1 is equal to 1. It means A1 is 1 time. So the value for N1 which corresponds to A1, it means 1, 1, 1. Here N2 is equal to 2. It means we have to go for the 2 times A2. 1, 1, minus 1. 1, 1, minus 1. And last one, N3 is equal to 1. It means E is equal to 1, 2 minus 1, 0. So 1 plus 1 plus 1, 5. So value 5, 2 and minus 1. So this is the reducible representation, and with the help of this equation we can convert this reducible representation into irreducible component. So dear students, this is the first example to convert reducible component into irreducible component. Now second examples of the same point group, the reducible representations TR to R is 301, and find out the irreducible component of this reducible representation. Okay, so we have to convert this reducible representation into irreducible representation. So we need a relation between reducible and irreducible representations, as well as we need a correct table. So with the help of that, N1 is equal to 1 upon H. The value for H is equal to 6. 1 plus 2 plus 3 is equal to 6. Okay, now reducible component is 3, 1 and 1, plus this reducible value for reducible representation is 0, 2 and 1, plus reducible component is 1, numbers of symmetry operation 3 is 3, and again 1. So is equal to 1 by 6, 3 plus 0 plus 3 is equal to 1. So the value for N1 is equal to 1. Value for N2, 1 by 6, N2 which corresponds to A2 irreducible representations. So 3 is the value for reducible representations, 1 is the numbers of that symmetry operation, and 1 is the character for irreducible representations. Plus reducible representation is 0, 2 is the numbers of that symmetry operation, and minus 1 is the character for that irreducible representation. 1 is the character for irreducible representations, plus 1 is the character for reducible representations. 3 is equal to numbers of that symmetry operations, and minus 1 is the character for that irreducible representations. 1 by 6, 3 plus 0 minus 3. So the value for N2 is equal to 0. And last one, that is the value for N3. 1 by 6. So character for reducible representation is 3. Numbers of that symmetry operation is 1. And character for irreducible component is 2, plus 0, 2 and minus 1. plus 1 is the character for reducible representation, 3 is the value for numbers of that symmetry operation, and 0 is the character for reducible representation. So is equal to 1 by 6, 6 plus 0 plus 0 is equal to 1. So the value 4 and 3 is equal to 1. C3V E twice C3, 3 sigma V. A1, N1 is equal to 1 times, it means A1 1 time. N2 0 means there is no involvement of N2. N3, it means E 2 minus 1 0. Value for N3 is equal to 1. So we have to mention only for 1 time. So these are the irreducible component for this reducible representation. So with the help of this equation, we can reduce any reducible representation into irreducible representations with the help of the character table of that point group. We are going for the next theorem is the great orthogonal theorem. Now, dear students, great orthogonal theorem is concerned with the element of the matrices and which constitute the irreducible representations. Okay, so what is great orthogonal theorem? Great orthogonal theorem is concerned with the element of the matrices which constitute the irreducible representations of a group. Now, the mathematical statement of the great orthogonal theorem is character rho summation of R T I R M N T J R M dash N dash. This is asterisk complex conjugation is equal to H by square root Li Lj delta mm dash delta Ij delta mm dash and delta nn dash. So this is the relation between reducible and irreducible. This is the mathematical statement of the great orthogonal theorem. So dear students, great orthogonal theorem is concerned with the element of the matrices which constitute the irreducible representations of a group. This is the mathematical statement of the great orthogonal theorem. Now, different term involved in this mathematical statement of the great orthogonal theorem. H represents order of a group. And we know that order of a group is nothing but the numbers of the symmetry elements are present in a molecule. Li and Lj. Li and Lj. It means these are the different dimensions of the dimension of that matrix. Li and Lj represents dimension of matrices. Now, this is the element of the, this is actually to IRMN. It means this is the element of the mth row and column of the ith irreducible representations. This is complex conjugation, or we can represent that this is the element of the nth row and nth column of the jth irreducible representations. Okay, so dear students, this is the mathematical statement of the great orthogonal theorem, and we can apply this equation in any irreducible representations of the group, the element of the matrices, components of a vector, and is orthogonal to each other, element in the same matrix, element of the corresponding irreducible representations. So anyhow, we can subdivide this great orthogonal theorem into three sub mathematical statement of the great orthogonal theorem. So first, mathematical statement of the great orthogonal theorem, character R, T I R, M N, T J, M dash N dash is equal to 0. Okay, we can apply normalized as well as orthogonality to the elements of the matrices. So here I is not equal to J. It means both these irreducible representations are different. So we can predict that element of the different irreducible representations of the corresponding matrices are orthogonal to each other. We know that this is the first irreducible representation, this is the second irreducible representations, this is the multiplication of any two irreducible representation, and summation is equal to 0. It means element of the different irreducible representations of the corresponding matrices are orthogonal to each other. Second characteristics or second mathematical statement of the great orthogonal theorem are TIR MN TIR M dash N dash is equal to 0. Here M is not equal to M dash, and is not equal to N dash. It means both have the same irreducible representation of the different of the corresponding matrices. It means element of the different sets of the matrices of the same irreducible representations are orthogonal to each other. So they are students, element of the corresponding matrices of the different irreducible representations are orthogonal to each other. And last one, character R, TIR, MN, TJ, R, M dash N dash is equal to H by Li. This equation can be satisfied if the value for here I is equal to J, and the value for delta delta ij delta dash delta nn dash is equal to 1. Now if you put the values, then what will happen? Li Lj, Li is equal to Lj. It means this is square root Li square. It means the value is Li, and value for delta ij delta dash delta nn dash is equal to 1. Then equation can be represented as H by Li. So dear students, this is the great mathematical statement of the great orthogonal theorem, and from the great orthogonal theorem we can subdivide a mathematical statement into three sub equations. So this is the these are the three sub statement of the great orthogonal theorem, and from the great orthogonal theorem we can derive the 5 characteristics of the irreducible representations. So let us start first uh, the characteristics of the irreducible representations. Characteristics of irreducible representations. From the great mathematical statement of the great orthogonal theorem, we can derive characteristics or properties of irreducible representations. Now, first characteristics or properties of the irreducible representations. First characteristics is the sum of the first characteristics, which is related to the numbers of the classes. Okay, so the numbers of the classes is equal to numbers of irreducible representation. So this is the first characteristics of irreducible representations. So dear students, numbers of the classes, or we can say numbers of irreducible representation is equal to numbers of classes. So first one is, first characteristics we can represent the numbers of irreducible representations of a group is equal to the numbers of the classes of the operations of the group. So first characteristics which represents numbers of the classes. So numbers of irreducible representation is equal to numbers of the classes of that group. So we can represent in case of C to A point group, it consists E C2 sigma V X Z and sigma V Y Z symmetry elements. Okay, so here E is conjugate to itself to form an individual class, C2 conjugate to itself to form an individual class, sigma V X Z conjugate to itself to form an individual class, and sigma V Y Z conjugate to itself to form an individual class. So here numbers of the classes is equal to 4, 1, 2, 3, and 4. So according to the first rule, the numbers of irreducible representation is equal to numbers of the classes of that symmetry operation. So we can represent that in case of C2V point group, E C2 sigma VXZ sigma VYZ. So numbers of the classes is equal to 4. It means numbers of irreducible representation should be equal to 4. So dear students, first characteristics or first properties of the irreducible representation is equal to the numbers of irreducible representations is equal to numbers of classes of that symmetry operation. Second characteristics or properties of irreducible representations. The sum of the square of the dimension. The sum of the square of the dimension is equal to order of a group. This is the second characteristics of the irreducible representations. So dear students, we can represent that the sum of the square of the dimension, the sum of the square of the dimension is equal to order of a group. So where I is equal to 1 to n. Now in case of C3b point group, E to YC3, 3 sigma b, A1, A2 and E. 1, 1, 1, 1, 1, minus 1, 2, minus 1, 0. Now here, the second characteristics of irreducible representation is the sum of the square of the character, the sum of the square of the dimension is equal to order of a group. Now in case of the ammonia molecule or C3b point group, order of a group is equal to 1 plus 2 plus 3 is equal to 6. Now character Li square is equal to 6. And we know that uh, dimension of any representation which corresponds to identity symmetry operations. So this is one dimension, this is one dimension, and this is two dimensional. Okay. So character for dimension of that irreducible representation is equal to 6. It means it should be just like a L1 square, L2 square plus L3 square is equal to 6. Now this equation can be satisfied if any two dimensions is equal to 1 and third representation is two-dimensional. Then and then these equations can be satisfied. Okay, so already it is given in the character C3b. So the second characteristics is the sum of the square of the dimension is equal to order of a group. Third one, third properties or third characteristics of the irreducible representations. The sum of the square of the character is equal to order of a group. What is the characteristic number 3? The sum of the square of the character is equal to order of a group. As for example, C3b point group, E to YC3, 3 sigma b, A1, A2 and E. 1, 1, 1, 1, 1, minus 1, 2, minus 1 and 0. If we take A1 irreducible representation, okay, according to the characteristics number 3, the sum of the square of the character is equal to order of a group. It means here the numbers of the symmetry operation is 1 and square of that character 1 square plus 2 is the numbers of that symmetry operation, 1 is the character of that representations, 3 is the numbers of that symmetry operation, and 1 is equal to 1 plus 2 plus 3 is equal to 6. So order of a group for C3b point group is 6. So we can represent numbers of the sum of the square of the character is equal to order of a group. This is the third law. Fourth law, the character of irreducible representations of the same group are orthogonal to each other. The character of irreducible representations of the corresponding of the same group are orthogonal to each other. As for example, if we take A1 and A2, A1 and A2, then what will happen? 1 into 1 into 1 is equal to 1, or we can represent that characteristics just like a R, character I into R, character J into R is equal to 0. It means the character of irreducible representations of the same group are orthogonal to each other. If we take A1 and A2, then what will happen? 1 into 1 into 1 is equal to 1. 1 into 1 into 2 is equal to 2. Minus 1, 1 into 3 is equal to minus 3 is equal to 0. It means this is the rule number 4 or characteristics number 4 or properties of the fourth characteristics of irreducible representations. The character of irreducible representations of the same group are orthogonal to each other. And last characteristics, the character of the element of the same class of an irreducible representations are the same. This is the characteristics number 5. So, dear students, with the help of this 5 characteristics of irreducible representations, we can derive the or we can construct the character table for C2V point group as well as in C3V point group as well as D2H point group and D3H character table, D3H point group. Now, what is character table? Character table is nothing but the devices can be utilized for the applications of group theory and molecular symmetry is known as character table. So to construct a character table, we need of 5 characteristics of irreducible representations. So first, construct a character table for C2V point group. Let us consider water molecule. It belongs to C2V point group. This molecule consists E, C2, sigma VXZ, and sigma V YZ symmetry elements. And it belongs to C2V point group. So, dear students, construct the character table for C2V point group. Let us consider water molecule. It consists E, C2, sigma VXZ, and sigma V YZ symmetry elements. It belongs to C2V point group. So, first, E is conjugated to itself to form an individual class. C2 is conjugated to itself to form an individual class. Sigma V XZ conjugate to itself to form an individual class. And sigma V YZ conjugate to itself. Therefore, here numbers of the classes is equal to 4. So, according to rule number first of the irreducible representations, numbers of irreducible representation is equal to numbers of classes. So, according to that, we can predict that C2V E C2 sigma V XZ sigma V YZ. T1, T2, T3, and T4. So here numbers of the classes is equal to 4, 1, 2, 3, and 4. So that should be 1, 2, 3, and 4 irreducible representations. So dear students, first characteristics of the irreducible representations, the numbers of the classes is equal to numbers of the irreducible representation is equal to numbers of the classes. Now, second characteristics of the irreducible representation, the sum of the square of the character is equal to order of a group. Suppose this one is the dimension L1, L2, L3, and L4. Okay, generally we know that dimension which corresponds to matrix representation for identity symmetry operation. So what is the second law? Second characteristics of the irreducible representations, the numbers of irreducible the numbers of the sum of the square of the dimension is equal to order of a group. So we can represent it as L1 square plus L2 square plus L3 square plus L4 square is equal to order of a group. Now in case of water molecule, order of a group is equal to 4. Now we know that dimension of any representation can't be a negative. So we can represent a minimum dimension is 1. A negative dimension cannot be possible. So if we take minimum dimension 1 square, 1 square, 1 square, 1 square is equal to 4. So 1 plus 1 plus 1 plus 1. 1 square plus 1 square plus 1 square is equal to 1 plus 1 plus 1 plus 1. So is equal to 4. That means dimension of these representations 1, 1, 1 and 1. Now to get the character for first irreducible representations, suppose this one is the character 1 C2. This is character 1 sigma V xz. This is character 1 sigma V yz. Okay. According to the characteristics number 3, the sum of the square of the character is equal to order of a group. The sum of the square of the character is equal to order of a group. So we can represent it as 1 into 1 square. 1 is equal to numbers of that symmetry operation. Again, 1 into character 1 C2 square plus 1 into character 1 sigma V xz square plus 1 into character 1 sigma V yz square is equal to order of a group. Okay. In case of water molecule, we know that order of a group is equal to 4. It means 1 plus character 1 C2 square plus character 1 sigma V xz square plus character 1 sigma V yz square is equal to 4. Okay. For the uniformity, first irreducible representation for all this character table should be with respect to plus 1. So if we take the value for character 1 C2 is 1, character 1 sigma V xz is equal to 1, and character 1 sigma V yz is equal to 1, then this equation can be satisfied. So we can take the values for character 1 C2, character 1 sigma V xz, character 1 sigma V with respect to 1. 1. So first irreducible representation is 1, 1, 1 and 1. To get the character for second one, suppose this is character C2 sigma V xz, character 2 sigma yz. To get the character for second irreducible representations, the fourth characteristics of the irreducible representations, the character of irreducible representations of any two irreducible representations are orthogonal to each other. So if we take T1 and T2, then what will happen? 1 into 1 into 1 is equal to 1 plus 1 into 1 into character 2 C2. Character 2 C2, it means 1 into character C2 plus 1 into 1 into character 2 sigma V xj plus 1 into 1 into character sigma V yz is equal to 0. Now this equation can be satisfied if the character for any representation is 1 and character for any two irreducible representations is equal to minus 1, then and then this equation can be satisfied. So if we take the values for character C2 is equal to 1, character sigma v y z is equal to minus 1, character minus 1, character for sigma v y z is equal to minus 1, then this equation can be satisfied. 1 plus 1 minus 1 minus 1 is equal to 0. So 1 minus 1 minus 1. Of the second irreducible representations, T2 is equal to 1, 1, minus 1, and minus 1. But this can satisfy the characteristics number 3. What is the characteristics number 3? The sum of the square of the character is equal to order of a group. So 1 into 1 square plus 1 into 1 square, 1 into minus 1 square plus 1 into 1 square, 1 into minus 1 square is equal to 1 plus 1 plus 1 plus 1 is equal to 4. So second irreducible representations is 1, 1, minus 1 and minus 1. Now to get the values for third irreducible representations, again we have to go for the characteristics number 4. The character for irreducible representations are orthogonal to each other. So if we take T1 and T3 first, and then T2 and T3. Suppose these values, character 3C2, character 3 sigma Vxz, character 3 sigma Vyz. Any two irreducible representations are orthogonal to each other. Or we can say the irreducible representations, the character for irreducible representations of the same group are orthogonal to each other. So if we take first T1 and T3, so 1 into 1 into 1 is equal to 1. 1 into 1 into character 3C2. 1 into 1 into character 3 sigma Vxz. 1 into 1 into character 3 sigma Vyz is equal to 0. Similarly, if we take T2 and T3, so 1 into 1 into 1, 1 plus character 3C2. 1 into minus 1 into character 3 sigma Vxz. 1 into minus 1, it means minus character 3 sigma Vyz is equal to 0. Now add equation first into second one. So what will happen? 2 plus 2 character C2 is equal to 0. It means character C2 is equal to minus 1. So character, the value for character 3C2 is equal to minus 1. Now substitute this value in above one equation. So 1 minus 1 character 3 sigma Vxz, character 3 sigma Vyz is equal to 0. It means character 3 sigma Vxz is equal to minus character 3 sigma Vyz. That means 1 is equal to minus 1. It means when the value for character 3 sigma Vxl is equal to plus 1, then the value for character 3 sigma Vyz should be minus 1. So if we take 1, it should be minus 1. Okay. Now these values can also be satisfied the value, the characteristics number 3. And what is the characteristics number 3? The sum of the square of the character is equal to order of a group. It means 1 into 1 into 1 square is equal to 1. 1 into minus square is equal to 1. 1 into 1 square is equal to 1. 1 into minus 1 square is equal to 1. So is equal to 4. It means the third irreducible representation is 1, minus 1, 1 and minus 1. Now to get the fourth irreducible representations, again characteristic number 4, the character of the irreducible representations of the same group are orthogonal to each other. So if we take first T1 and T4 and then T2 and T4 to get the two equations. So first one T1 and T4. So to get 1 into 1 into 1, 1, 1 into 1 into character 4 C2, 1 into 1 into character 4 sigma Vxz, 1 into 1 into character 4 sigma V yz is equal to 0. Then T2 and T4. T2 and T4. So 1 into 1 into 1 is equal to 1. 1 into 1 into character 4 C2. 1 into minus 1 character 4 sigma V xz. Again minus 1, it means character 4 sigma V yz is equal to 0. Now add equation 1 into 2. Suppose this one is 1 and this one is second. So 2 plus 2 character 4 C2, both are cancelled out, is equal to 0. It means character 4 C2 is equal to minus 1. Again the value for character 4 C2 is minus 1. Now substitute this value in above one equation. So 1 plus minus 1 plus character 4 sigma V xz plus character 4 sigma V yz is equal to 0. It means character 4 sigma V xz is equal to minus character 4 sigma V yz. So we can represent it as minus 1, 1 is equal to minus 1. So the value for character V sigma x is equal to plus 1, then it should be minus 1. We already take that one. So if we take the value for character V sigma x is equal to minus 1, it should be character 1. So if we take minus 1 and 1, then this representation should be satisfied the characteristics number 3. The sum of the square of the character is equal to order of a group. It means 1 into 1 square is equal to 1. 1 into minus 1 square is equal to 1. 1 into minus 1 square is equal to 1. 1 into 1 square is equal to 1. So the value is equal to 4. So fourth irreducible representation is 1 minus 1 minus 1 and 1. So remaining portion is the Mulligan symbols. Now how to get the Mulligan symbols? If any representations is one dimensional, then capital A or capital B can be used. If the value for main principal axis is equal to plus 1, capital letter A can be used. And if the character for that main principal axis is -1, so capital letter capital B can be used as a Mulliken symbol. For the two-dimensional, T can be used, E can be used, and for the three-dimensional, T or F can be used. Okay, now here, this is one dimensional, this is one dimensional, this is again one dimensional, one dimensional. So A or B can be used. So when A and when B, we already discussed. So here the value, this is the main principal axis C2. So here character is 1. So later A can be used. Here one dimensional A can be used. -1 means B can be used. B. Now next one, subscription. Just like a A1, A2, B1, B2. Here only one principal axis is C2. And here no perpendicular axis other than C2. Okay, so according to the rules, C2 is present and that perpendicular to the main principal axis, and character for that C2 is +1, then subscript 1 can be used, and character is -1, then subscript 2 can be used. But here only one C2 is there, so we have to go for the next one, that is sigma V extend. If the value for that character is +1, then subscript 1 can be used, and -1, then subscript can be 2 can be used. So here character is 1, it means subscript 1 can be used. Here -1, then subscript 2 can be used. +1 means 1 and 2. So these are known as a Mulliken symbols. So anyhow, dear students, this is the derivation for C2V point group, or we can say construct the character table for water molecule, sulfur dioxide molecule, or H2S molecules. All are the same. Okay. Now next one is construct a character table for C3V point group. Let us consider ammonia molecule. It belongs to C2V point group. It belongs to C3V point group. It consists E, C3 plus, C3 minus, sigma Va, sigma Vb, and sigma Vc symmetry elements. We know that E is conjugate to itself to form an individual class. C3 plus C3 minus conjugate to each other to form a combined class. Sigma Va, sigma Vb, sigma Vc conjugate to one and form a combined class. So here numbers of the classes is equal to 3. So according to the rule number first, the numbers of irreducible representation is equal to numbers of the classes. So here 3 class means numbers of the irreducible representation should be equal to 3. C3V, E, 2C3, 3 sigma V. Here E is conjugate to itself to form an individual class. C3 plus C3 minus conjugate to each other to form a combined class. Sigma V, sigma Vb, sigma Vc conjugate to one another to form a combined class. Okay, so irreducible representations can be represented as T1, T2, and T3. Now, according to the rule number second, the sum of the square of the dimension is equal to order of a group. Suppose dimension of this representation is L1, L2, and L3. The sum of the square of the dimension is equal to order of a group. L1 square, L2 square, plus L3 square is equal to order of a group. So in case of ammonia molecule or C3V point group, the order of a group is equal to 6. Now this equation can be satisfied if the dimension of any representations is 1, Any two representations, 1 and then 2 for the third representations. So this equation, so these values can be represented as 1, 1 and 2. To get the first irreducible representations, character 1 C3, character 1 sigma V. The second characteristics of the irreducible representations, the sum of the square of the character is equal to order of a group. This is the third characteristics of the irreducible representation. So 1 into 1 square, 1 plus character 1, sorry, 2 into character 1 C3 square plus 3 character 1 sigma V square is equal to 0. Sorry, is equal to order of a group is equal to 6. Now this equation can be satisfied if the value for character 1 C3 is 1 and 1. To maintain the uniformity of the of any character table, first irreducible representation should be with respect to plus 1. So 1 and 1. To get the second irreducible representation, this is the value for character 2 C3, character 2 sigma V. According to the rule number 4, the character of second rule number 4, the character of the irreducible representations of the same irreducible of the uh, same group are orthogonal to each other. The character of different irreducible representations of the same group are orthogonal to each other. It means if we take T1 and T2, then 1 into 1 into 1 is equal to 1. 2 into 1 into character 2C3 plus 3 into 1, it means 3 character 2 sigma V is equal to 0. This equation can be satisfied if the value for character 2C3 is equal to 1 and character 2 sigma V is equal to minus 1. So 1 plus 2 into 1 plus 3 into character minus 1 is equal to 0. It means second representation should be 1 and minus 1. But this can be satisfied the characteristics number 3. What is characteristics number 3? The sum of the square of that irreducible representation. Now to get the third irreducible representations, we have to go for the rule number 4. Any irreducible representations, the character for the rule number 4, the character of the irreducible representations of the same group are orthogonal to each other. So if we take T1 and T2, T1 and T3 first, and then T2 and T3 to get the two equations. So 1 into 1 into 1 into 2, 2, 2 into 1 into character 3, it means 2 character 3 C3. 1 into 1 into 3 character 3 sigma V is equal to 0. Similarly, if we take T2 and T3, then 1 into 1 into 2, 2, 2 into 1 into character 3 C3, 1, 3 into minus 1, it means minus 3 character 3 sigma v is equal to 0. This is equation number 1. This is equation number 2. Add equation 1 into 2. So 4 plus 4 character 3 C3, this cancel out, is equal to 0. That means character 3 C3 is equal to minus 1. Minus 1. Now to get the third one, if we substitute this value in above one equation, so 2 minus 2 plus 3 character 3 sigma v is equal to 0. It means character 3 sigma v is equal to 0. So the third irreducible representations can be represented as 2 minus 1, 0. Now Mulliken symbols. We already discussed that any representations is one dimensional, so capital A and capital B can be used. Here the character for main principal axis is 1, so A can be used. Here 1, A can be used, and this is two dimensional, it means E can be used. And there is only C3 plus and C3 minus at present, so there is no C2 is present in these representations, so we have to go for the next one. So here the value for character sigma v is equal to 1 plus 1. So subscript a1 can be used, 2 can be used, minus 1, 0, it means there is no 2. So this is the character table for C3b point group. Now, how to explain the character table? Now, how to explain the character table or how to explain different areas of the character table. We already discussed the area number one. Area number one represents different characters by operating different symmetry operation. Okay, so area number one represents different characters of a different symmetry operation. Area number two, the top of the left corner of the character table represents symbols for the point group according to the showing flash method. Area number two also represents Mulliken symbols. We already discussed that if the value for character of main principal axis is 1, then letter A or letter B, sorry, A and B, one dimensional A or B can be used. If the character for main principal axis, so dear students, if dimension is one dimensional, capital letter A or B can be used. And if the representation is two-dimensional, E can be used, and for the three-dimensional, T or F can be used. If the character for main principal axis is 1, in case of the one-dimensional, A can be used. If -1, then capital letter B can be used. Then C2 is present as a main principal axis and C2 is present as a subsidiary axis. If C2 is perpendicular to the main principal axis and character of that matrix is of that representation is +1, then subscript 1 can be used. Otherwise, -1, then subscript 2 can be used. So anyhow, if our group consists the sigma h and the value the character for that sigma h is equal to +1, then single prime can be used. It means a1 dash, a2 dash, etc. So single dash can be used. And if character for sigma h is equal to -1, then double prime can be used. Similarly, if our group consists I symmetry elements, then the value for that sigma character I is equal to +1, then subscript G can be used, and character is -1, then subscript U can be used. So dear students, these are the informations regarding the Mulliken symbols. Okay, so area number one represents, these are the characters for different irreducible representations by operating different symmetry operations. Area number two represents Mulliken symbols. Area number three. Now, area number three, these are the informations regarding the p orbitals. X, Z represents pz orbitals, px orbital, and py orbitals. It means if we operate uh, a different symmetry operation on pz to get the different irreducible representations. So if we operate different symmetry operation on px to get the different irreducible representation. So area number 3, which represents or which corresponds to p orbitals, and area number 4 represents d orbitals, or we can say transformation properties. Dx square minus y square, dx square plus z, dx square plus y square, dz square, dxy, dxz, dyz, etc. So dear students, this is the explanations of the character table. So dear students, I think this is the enough for today's discussion. Now, thank you very much for listening me very silently. Uh, we will meet on the next lecture. So, madam, can we finish this session? Hello.
Yes, sir. Yes,
Okay.
sir. Yes, sir.
Thank you, madam.
Thank you so much, sir, for facilitating such a positive learning environment. We really learned a lot, sir, and we are eagerly looking forward for your upcoming session on this topic. My sincere gratitude to all the participants, and we will back soon with upcoming session. Goodbye, everyone. Have a nice day. Goodbye, sir.
Thank you. Thank you. Have a nice day.